Recording has started.
Let's jump right into stuff this morning. Yesterday we kind of stepped back a little bit and worked on reviewing our areas and volumes and surface areas. And we did a little bit with our finding measurements to the feet, inch, and the desired fraction of an inch. Today we want to look at something that's specific to machining. The first part we've looked at a little bit already, and that is the idea of tolerances or allowances in both interference and clearance fits. So if I'm looking at this, if this pin here is given as 0.250 inches plus or minus 0.03 of an inch. And this hole down here is given as 0.242 inches plus or minus 3 again. I want to see if you remember how to find the minimum and maximum interference. So take a few minutes, figure that out for me, and then we'll go over it. Let's take a peek, see how it's working out for you. So to find the minimum and maximum interference, we look at both the pin and the hole, and we find the minimum and maximum size. So for the pin, what is the minimum size of the pin?
47.
247, good. What is the maximum size of the pin?
53.
253, good. For the hole, what is the minimum size of the hole?
39.
239, and the maximum?
45.
245. So for the minimum interference The minimum interference occurs when the pin is its smallest and the hole is its largest. What's the difference between those?
2,000s.
2,000s. Good. The maximum interference occurs when the pin is its largest and the hole is its smallest. How much interference is there?
4,000s.
Careful.
4,000s.
14. There we go.
Oh. Okay.
39 to 53.
I missed
So
that.
yeah, I knew what you were thinking. Yeah, you had her. So 14,000. So you can see, even to the plus or minus 3,000, that's still quite a large range for our interference. Now let's look at a slide. Obviously, for the slide to work, there has to be some clearance. Let's say this slide is 0.625 inches, plus or minus. Let's go down to 2,000ths. And the groove that it is running in here is 0.630 inches, plus or minus 2,000ths. So again, find for me the minimum and maximum clearance for this. So as we look at this one, for the slide up here, what is the minimum width of that slide?
Oh, minimum. 23.
623. Very good. What's the maximum width of that slide?
27.
627. Good. For the slot, what is the minimum width?
80.
628. And the maximum?
32.
632. So for our clearance, the minimum clearance comes when the slide is large and the slot is small. What's the difference between those? 1,000. The maximum clearance comes when the slide is small and the slot is large. What's the difference there?
10,000.
9. Good. So the interference and clearance fits, again, when you have two parts that fit together, you've got to be very, very careful with your allowances and tolerances. This is what is called traditional rectangular tolerancing. The industry moved, close to 20 years ago now, to something called geometric tolerancing. Or geometric dimensioning and tolerancing, GD&T. In geometric dimensioning and tolerancing, the way the tolerancing is created depends on the use of the part. I'm not going to get into it a whole lot here, but if you have let's say you've got a location of a hole in a part, rather than saying that that center of that hole has to be in a certain range this way and a certain range that way, because what that does is it gives you a rectangle. The center of that hole has to be within that rectangle. Well, when you look at that rectangle, you see that from the center out to the corners, it's a lot further than from the center just out to the flat side. So why is it okay to be, let me draw it larger here. So there's our center, and let's say we can be off this far in that direction and this far in that direction, creating that rectangular allowable location. Well, why is it okay to be off this far if we're going at an angle, but only this far if we're going straight? So in geometric dimensioning and tolerancing, rather than giving a plus or minus for the x and a plus or minus for the y, they give what's called a runout or circular runout. Where they say that we have to be within this distance of the center no matter what the direction is. So rather than giving a plus or minus in the x and y, we give a radial distance from that desired ideal location. Okay, so our other half of the material for today is talking about gauge blocks and gauge blocks buildups. I don't know, have you guys seen the gauge blocks in the shop yet? Has Richard gone through any of those with you? Yep. Okay, so building them up to make very, very precise heights. In the spring, we're going to look at angles and sign blocks and how you can create a very precise angle with that sign block if you have an exact height. A sign bar is just a bar that's very precisely machined. Has an exact distance of either 5 or 10 inches between the centers of those circular ends. And we can use it to create a very exact angle. If I have the exact height built up here, that height is built up using gauge blocks. For standard gauge blocks, or English gauge blocks are sometimes called. We have 3 different series of blocks. There's the 9 block series, that is the tenths or the 10,000th of an inch series. In this series, because it's a 10,000th of an inch, is too small to just make by itself. It would be literally hair thin. So what we do in this series to make it work is we have it 1/10 of an inch plus the 1/10,000. So I have 100 thousandths plus a tenth. 100 thousandths plus 2/10. And down the line, all the way up to the 100 thousandths plus 9/10, like that. Our next series is a 49 block series. And this is the thousandths. So in this series, still 1,000th of an inch would still be too small, too thin to be durable. It would get bent rather easily. It'd be foil thin. So in this series, we still put 1/10 of an inch with it. So it's not just 1,000th, it's 101,000. 102,000. And this goes up to 149 thousandths of an inch. So there's 49 of them, 101 to 149. Next, then we have a 19 block series, which is going to be our 100th of an inch. But rather than going to an individual 100th, we tend to go in 50s. Since the other block goes to 49, we can go in 50s here. So now we don't need the 1/10 of an inch with this. 50 thousandths or 500ths, it is thick enough that it can stand on its own. So this would be 50 thousandths, 100 thousandths, 150 thousandths, all the way up to 950 thousandths, 50 thousandths at a time. And then our final series is just the whole inches, 1 inch, 2 inch, 3 inch, 4 inch. So if I need to build something that is precisely, now precisely I mean to the 10,000th of an inch, 2.438, let's go 2.4386 inches in size. What we do is we start working with the last digit, the 6. In order to build that 6, there's only one gauge block in our set that will give us 6 10,000ths or 6/10. And that is, of course, up here. That block is going to be 0.1006 inches. So what we have to do is we have to subtract that block and see what's left. There's 2.338 left. So we're going to assume that block is in our buildup. Next, we look for 2 things, actually, in the next stage. We have to find this 8, but we also need to look at this piece here. That is a 3, so we're going to try to get rid of both of those at once. If that were 5 or larger, we would try to bring it down to 5. But since it's smaller than 5, we're going to try to take this one down to 0. So what we're looking for is something that has a 38 thousandths in it. Well, that's going to be in our 49 block series. There'll be a block here that's 0.138. So that's the block we're going to use. So we subtract that, we are left with 2.200 inches left. So that block is part of our buildup. Now we just need to get rid of the remaining decimal, the 2/10 of an inch, or the 200,000ths of an inch. In our 19 block series, we have one here that is exactly 200 thousandths. That's the one we're going to use. Subtracting leaves us with 2 whole inches. So we have the 200 block goes in, and we have our 2-inch block. So this buildup, we tend to list them backwards when we list them out, is the 2-inch, the 200, the 138, and the 106/10. Those are the 4 blocks that would make that buildup. So we start again at that smallest digit, that last digit, and work our way backwards to build those up. In your notes, let's do 10784 inches. Find the buildup for that for me. So we'll start again with our 10,000th. The only one that has a 4 in that last digit is the 1004. We subtract that out, and we are left with 0.978 inches. The next block is going to have to have an 8 in the end, but it's a 7 here. So we need to both get rid of the 8 and bring this 7 down to a 5. That'll be the 0.128 inch block that we'll use for that. That's going to bring us down to 0.850. And there actually is a block that is 0.850, 850. So those are the blocks we're going to use, the 850, the 128, and the 100.4, or 104/10. Now this example brings us to, what if what we wanted to build was simply 0.0784? Well, we cannot build that. It's too small. The smallest block we have in our set is the 50 thousandths here, the 500ths. We could do the 50 thousandths out of that, but there is no way to get the 4/10ths or the 4/10,000ths without having a tenth with it. That's the only block we have that has the 4/10ths in it. So there's no way we can build up 0.0784. In fact, even if it was 0.1784, we can't build it. Because we would have the 1004, or the 100.4 For the first block, leaving us with 0.078 to build. Well, the only thing that has an 8 in the thousandths place is in the 49 block series here. And in that series, they still all have a 10th. I would have to put in there, I'd want a 28 there, but it's a 128. There is no just 028. So I can't build that either. If I needed to build something like a 0.1784, there would actually be a decision to make. If I really needed to build that, and if my tolerance, my need for precision wasn't that great, the only way I could even come close to building that is if I rounded it to 0.178. Now from there, I can build it because I can put in 128, which brings it down to 50. And so I could use the 128 out of the 49 block series and the 50 out of the 19 block series. So there are limitations to these gauge blocks. Even though they are very versatile, there are some limitations. Now we also have metric gauge blocks. For our metric gauge blocks, we go down to 1,000th of a millimeter. And our first series, our 9-block series here, actually all of our series for metric are 9 blocks. And our first series is 1 whole millimeter plus 1,000th, 1 whole millimeter plus 2,000ths, up to 1.009 millimeters. Our second series goes to the 100th, but it's still 1 plus 100th, 1 plus 200ths, 1 plus 900ths. Our third series, this one, the 10th of a millimeter was still too thin to make a reliable block. It would have been, again, foil thin, so it would have not stayed straight for us. So it's 1.1, 1.2, up to 1.9. And then we have whole millimeters, 1, 2, all the way up to 9. And then we have 10, 20, all the way up to 90 whole millimeters. So if I want to build a measurement like 4.93 millimeters, we do the same thing. We start with the 3. Well, there's a 1.003 here in that first series. That gets rid of the 3. We're at 3.390. Next, we're going to focus on the 9. We have a 1.09. Take that one out. We're at 2.3. Next, we'll focus on the 3. Well, there's a 1.3 in here. We take out the 1.3, leaves us with exactly 1. And of course, we do have a block that's exactly 1 millimeter. So we can do our gauge block buildup. Because I gave you that quiz yesterday, that quiz 10-11. By the way, it says it's due at noon today. I'm going to push that back to noon Friday. Just because I know that last problem, 9 through 12, that hammer is a tough problem. I want to give you plenty of time to make sure you have time to go through that. A little bit easier assignment today in Blackboard. There is a packet. I believe it has 12 pages. In that packet, there's a section on tolerances, and there's a section on gauge blocks. So have your work on those for your homework for today. So I'm taking it easy on you today. Anybody have any questions? Okay, well, if you want to stick around and work, I will be online here for a while to answer any questions that come up. Otherwise, if you want to, you